Many of our most critical medicines lose effectiveness just when they are most needed. That's when a patient is most vulnerable to an infection or a cancer. Penicillin was once a blockbuster medicine, but is no longer. This loss of effectiveness is due to drug resistance, when the disease no longer responds to the medicine being used to treat it. You've probably heard about antibiotic resistance in the news, superbugs, or when a loved one's chemotherapy fails. The changes that confer drug resistance impact every antiviral drug, HIV, hepatitis C, and even the flu, and is currently a challenge in the development of medicines for COVID-19. My name is Celia Schiffer, and I'm a professor of biochemistry and molecular pharmacology at the University of Massachusetts Medical School. I'm also the founder and director of the Institute for Drug Resistance. In my research, we are developing drug design strategies to preemptively avoid drug resistance. Our goal is to make medicines that last and can better treat infections and cancers. Let's talk about infections for a moment. In an infection, the body is invaded by a germ, for instance, a bacteria or a virus. This germ's goal is to copy itself or reproduce as quickly as possible. To reproduce, the germ uses a series of tiny machines called enzymes. These enzymes are essential for the germ to survive. Thus, to stop the germs in the design of modern medicines, we block these enzymes and disrupt the germ's ability to reproduce. This is the way we make a new antibiotic or antiviral drug to target a virus like COVID-19. In fact, many of the 8,000 FDA-approved medications that we take for the treatment of infections or even cancer stop just one specific enzyme. In the past, early drugs like penicillin were found almost by accident. Today, when we scientists design new medicines, we look at how these enzymes work in atomic detail. We then design medicines to stop the enzymes from working. It's much like jamming a rod into a machine's critical gear. This process, called structure-based drug design, has led to many new drugs. Sounds easy enough, right? Well, for medicines aimed at an infection or cancer, the story often doesn't end here. The germ or cancer cell is always trying to reproduce and grow. If something is blocking that growth, the germ tries to get around it by changing. This change is called evolution. Evolution is the pressure of life to find a way for the biology of the system to keep growing, and if the growth is being blocked by a drug, evolution leads to drug resistance. Evolution changes the molecular machines in ways that allow them to continue to carry out their job, but no longer be stopped by the medicines. These changes alter the machine's structure and ability to bend and flex in a way that gets around the blocking medicine. These changes can happen where the drug blocks activity or even far away from the position, interfering with a hinge or joint in the enzyme in such a way that the enzyme can keep working, but the medicine no longer blocks it. So what can we do to design better medicines? The trick is to understand how the molecular machines work in such a way that there is no easy way for evolution to get around it. Think about damming up a river. If you put your dam up where the river is flowing through a flat field, the water can easily find a way around your dam. Instead, strategically building the dam where the river is flowing through a narrow canyon is much more effective, as the water can't easily find a way to flow around the canyon. In my lab, when we design medicines to avoid drug resistance, we strategically look for those narrow canyons to place our dam. We are looking for parts of the enzyme to block so that evolution cannot easily cause drug resistance. As we invest in the health of our future, we want to design medicines that continue to work and last and evade drug resistance.